Hello. Mhm. Okay, so let's get started. Today's topic is electromagnetic induction. It's considered one of the hardest topics in physics, at least in physics A levels and physics GCSE. It's also one of my favorite topics, and I'm really enthusiastic when it comes to electromagnetic induction, because once you understand it, doesn't happen instantly, but once you understand it, it's amazing. So yeah, let's start. So we'll start with Faraday's law, and we'll start with something that is called the flux, the magnetic flux. So if you have a magnetic field, let's say you have a magnetic field, and its direction down, B. B is sometimes called the magnetic field strength. That is incorrect. It's magnetic flux density. Magnetic flux density. And it's measured in Tesla. Tesla. So 1 Tesla is a very strong magnetic field. Just for reference. 1 Tesla is a very strong field. Okay. If you take a loop, it doesn't have to be a loop of Y, it's a loop of anything, just an area, an invisible area, like in space. And if you multiply the magnetic flux by the area of that loop, that gives you a magnetic flux through the loop. So flux is B times area. However, if the area is not perpendicular to the magnetic lines, that means you're catching less of the magnetic flux. So let's say the area is like this, and the area is positioned like this, and the fields are going at an angle. That means you're not catching all of the field. So you multiply it by the cosine of the angle, where theta is the angle between the field lines and the normal to the area. Does everything make sense so far on a scale of 0 to 10? Please let me know. Is everything making sense? Okay, good. So cosine, we multiply by cosine theta, and that's the angle between the normal vector. Let's take the normal vector like this to the area and the vector of yes, if you consider that A is a vector, right? But A is an area. But technically, yes, you can. It is. You just need to accurately define area, the vector A. So A is a vector. Question mark. Well, yes, if you define that vector accurately. Okay, and the Faraday's law of electromagnetic induction says that a loop of wires will act as an EMF, or in other words, an EMF will be induced in the loop if the flux is changing. So Faraday's law, Faraday's law, an EMF will be induced in the loop if the flux is changing. If the flux is changing. Sorry. Flux. Yeah, the flux is changing. Okay. So basically, in this loop, okay, sorry. Let's not get ahead of ourselves. And the EMF induced in the loop is minus d phi dt. That's Faraday's law. It was Faraday's genius. Absolute genius. How he got to that conclusion. And yeah. So how can you change the flux? I remind you, the flux is BA cos theta. So if you have a loop of wires in a magnetic field, how can you change? How can you induce an EMF in the coil? Give me some options. Can you change B? Yes, change B. That works if you take a magnet and you have a loop. You have a magnet and a loop. And you move the magnet closer to the loop, further away, closer, further, closer, further. That's you're changing B. Move the charges, but what does that change if you move the wires? If you move the wires, that also changes B, right? It changes the flux because you're moving the wires further away from the magnet. That means B increases. So that's also changing B. So moving wires and moving the magnet is the same thing. What else can you do? Yeah, change the area. If you change the area, no, that's changing the area in this particular case. Change area, or change the angle. Change theta. Usually that means rotate. If you rotate the coil, that will induce an EMF in the coil. Now, I said before that it doesn't have to be a loop of wires. So will an EMF be induced if it's, I don't know, made of wood? What do you think? Will an EMF be induced if it's Why not? No free electrons. That's a valid point. No free electrons. Honestly, I don't think I don't have a definite answer for you. No, I do. It will be induced. It's just there won't be any free electrons show to show that. So the free electrons won't move. You won't be able to measure a voltage, and you won't be able to measure a current, certainly. So you kind of the EMF will be there, but there was no way to show it. It's like if a tree falls in a forest and no one's there to hear it, does it make a sound? So if the flux is changing, but there are no free electrons to register that, is an EMF actually induced? Well, it must be induced. Yeah, if you take Maxwell's equation, then it must. It's not specific to wires. So yeah. Okay, the Lenz's law. Lenz's law is actually that little minus. So if you write down Faraday's law, that the EMF is minus d phi dt. I'm not doing the flux linkage thing. The flux linkage is obvious. You just plug an n in front, and that's it. That little minus here is Lenz's genius. So Lenz's law. Lenz's law. So what it says that the EMF is induced in such a direction as to oppose the change that that induced the EMF in the first place. The EMF is induced in a direction as to oppose the change in flux that induced the EMF in the first place. And this is a mouthful. However, let's look at a simple example. Let's take a loop of wires and a magnet, north and south. The lines from the magnet, they go like this. So as the magnet is moving down, the magnetic field is going down, B is increasing. So that's an example. As the B is increasing, a current will be induced as to oppose that increase. A current will be induced in the loop as to oppose that increase. What does that mean? What that means that the magnetic field of the loop will be upwards. So the magnetic field of the loop is upwards. What kind of current would produce an upwards field? A clockwise or an anti-clockwise? Using the right-hand rule, yes, using the right-hand rule, the current would be induced in an anti-clockwise direction. So the loop will produce an upwards field. The current is anti-clockwise. Does that make sense? Do you understand? On a scale of 0 to 10, please. Okay. So if you increase the field, if you increase the flux, the loop will try to decrease the flux. How can you decrease the flux? By producing a magnetic field in the opposite direction. Now, if the magnet is moving up, let's look at a magnet moving up, north, south. So there's a field down, and their magnet is moving up. So B is decreasing. The loop will try to build up the decreasing field. The decreasing flux, of course. Sorry, I'm using Greek letter for flux. Decreasing flux. And that means it will produce a downwards field. It will produce a downwards field. So that's the field of the loop. And that's the field of the magnet. Because it doesn't like change. The loop doesn't like change. It produces a downwards field, which so the current would be clockwise. So hence a clockwise current. And that's it. Okay, so hopefully you understand this. By the way, it's not just the magnetic flux density you can change. You can change the area, and the effect would be the same. If you, for example, make the area bigger, that's increasing the flux. Oh, because a current produces a magnetic field. If you have a current in a loop, it produces a field. Does that answer your question, Caitlin? Okay. All right, so let's have a look at this example, problem 2. The current I in the conductor wire is decreasing, which induces currents both in loops Y and Z. So first of all, why the fact that the current is decreasing, it induces a current in Y and Z. So Y and Z are just loops of wires. Can somebody tell me? The magnetic field decreases. Yes, there is a magnetic field because there's a wire. Yes, there's a magnetic field around the wire because any wire produces a magnetic field. Magnetic field. around a wire. That's we've done a couple of weeks ago. So around the wire, there is a magnetic field. So if you place a loop here, there will be a flux through the loop, where B times area. Flux is B times area. And if you place a loop here, it will be flux is B times area. Okay, so there's a magnetic field going into the page and magnetic field going out of the page here. So, can you please try to answer this question? Maybe as a direct message. Can you just send me a direct message? Can everyone do that? Just with the letter? Okay, I got 2 replies so far. Okay, 3 replies. I'm waiting for 3 more. If you don't know, just say don't know. But I'd like to receive an answer from everyone. I haven't received a... Okay. Okay. Just one more. Who am waiting for? 1, 2, 3, 4, 5, 6. Julian. Julian, what do you think? Okay. Right. The correct answer is B. Correct answer is B because, and most of you got that one right. Ah, that's fine. Yes, that's the multiple choice. So let's see. This is there's a magnetic field. So red is the magnetic field of the wire. Red is the field of the wire, and it's going into the page. And here it's going out of the page, magnetic field of the wire. Now that field is decreasing. B of the wire is decreasing. That means the loop will try to build up that magnetic field. So the loop will produce a magnetic field into the page. And that's magnetic field of the loop. And to do this, it has to have a clockwise current. So a current will be induced clockwise to increase the decreasing field. On this side, once again, the field is decreasing, so you would try to build up that field by producing a current in the anti-clockwise direction as to build up the decreasing field. Does that make sense on a scale of 0 to 10? Do you understand fully? You use the right-hand rule to find the direction, yes? So around the loop. On a scale of 0 to 10, please. Just as a... All right. Okay. Lovely. Okay, problem 3. Problem 3. So problem 3 has two different solutions, and I'm going to go with both. Solution 1. First, motional EMF. And that's the easy one. If you consider this wire, and it's moving with velocity v. Consider a single electron inside this wire. A single free electron. It's a single free electron. Now, there is a magnetic field going out of the page. So magnetic field going out of the page. The fact that the electron, so that's the magnetic field, the electron is moving to the right means there's a current to the left. So a moving electron is current. But the electron is moving to the right, therefore the current is going to the left. So it's a current to the left. And now we use the left-hand rule. So field going out of the page, current going left, and the force will be up. So there's an upwards force on the electron. What that means that the top of the rod will become negatively charged because electrons will be pushed to the top, whereas the bottom will become positive because the electrons have left to seek a better life on the top end of the rod, or some of the electrons, the ones that have the most energy. And you will have so that is a magnetic force that pushes the electrons up. Will be an opposite force because there's an electric field now. The electrons are now at the top and they're pushing the remaining electrons down. We have went up to seek for a better life. You guys, you stay put. You stay where you are. Because we have a strong electric field, we push them down. So any electron that tries to climb up the social ladder will be pushed down by their fellow electrons who got there first. I'm a hoot today on metaphors. Okay. So this is a magnetic force upwards, and that's an electric force downwards. Does everything make sense so far? Please ask me a question if you don't understand. We've considered a single electron inside the wire. As it is moving, it will be pushed up by the magnetic force, by the Lorentz force. As more and more electrons move up, they will gather at the top, producing an electric field upwards. Well, there will be an upwards electric field, which would push the electrons down. So electrons would be repelled from the top. So any electron inside the wire is now in equilibrium. There's a magnetic force up and the electric force down. The magnetic force is QVB, and the electric force if they're being pushed down, Well, no, they won't be in equilibrium, because if you neutralize them, then there's no electric field to push against the magnetic force, so the magnetic force will push you back up again. So it has to be in equilibrium because the magnetic force is balanced by the electric force, and the electric force is Q times E, where E is the electric field inside. If you know anything about the electric field, if this is the distance L, this is the length of the wire, then the magnetic electric field is Q V, the voltage, well, EMF. So if you connect a voltmeter, effectively, what happens now? If you were to connect a voltmeter across the ends, you would register a voltage. And that voltage is the EMF of the wire. So EMF divided by the length, because that's the capacitor equation. If you have the distance between the capacitor and the uniform electric field, then the electric field is voltage divided by the distance. Okay, so now we have QVB equals QE over L. Q cancels, and the EMF is VBL. It's a beautiful result. This is called the motional EMF. If you have a metal wire moving through a magnetic field, a voltage across the ends would be VBL. Now, I want to arrive to the same result by considering the flux. So 2. Flux. Right, so to do this, I will draw this. I'll copy this picture. And I will realize that there's an area. This is an area inside a magnetic field. Area A is an area, and B is the field. So the flux would be BA. Okay. Now, this rod is moving, and in time t, it moves a distance vt. In time t. In time t, rod moves vt. So the area decreases by Vt times L. It means that the rate of decrease of area is, well, VL. So d phi dt is dBA dt. B is a constant, so B dA dt. And dA dt is VL. BVL. Well, yes, technically it would be minus. And that would be minus BVL. and EMF is minus d phi dt, which is BVL. The minus really doesn't matter here because, well, what is a positive EMF? You have to define. Why is the area decreasing? Because the area was like this, and now it's like this. For a few seconds later, it would be like this. The area is decreasing because you're swiping the area. Oh, that was bad. So that area between, which is inside the loop, is decreasing. The rate of change of that area, so the EMF induced in that loop is VBL, which is the same result. You see, we got the same result using two different methods. I honestly like the second method more because the first one is not you're not talking about the flux at all. But yeah, the minus here is very arbitrary because what is a negative EMF? You have to define what a positive and a negative EMF is. So my advice when you're doing problems like this, just forget about the minus, just do the magnitude, and then you work out the minus. Okay, so now to work out the minus, which way will the current be? So there's a field through the loop, and it's out of the page. Now the flux is decreasing because the area is decreasing. So area is decreasing. So a current will be induced to increase the flux. So the current will be induced in an anti-clockwise direction. So the current would be anti-clockwise. Anti-clockwise current. At this stage, on a scale of 0 to 10, does everyone understand clearly why the current is anti-clockwise? This is very important. Yes or no? Do you understand why the current is anti-clockwise? I expect an answer from everyone. Okay. Okay, Abiola is asking a very good question. Yes, there's a right-hand rule for a single wire, and there's a right-hand rule for a loop. Right-hand rule for a loop. So the right-hand, in this case, the fingers is the field. Fingers is the field. And this is the current. The thumb is the current. Here, the fingers are the current. If you have a loop of current, and the thumb is the field B. So you can use the right-hand rule in two different ways. If you have a loop with a current, you use the fingers as the current, and the thumb is the field. And if you have a wire, the thumb is the current, and the fingers are the field. Does that make sense, Abiola? Okay. Yeah, so here the thumb is the field, which is out of the page, and the fingers go anti-clockwise. Good. All right, so the question is, what is the maximum power output of the bulb? Okay, let's check your knowledge. Work out this multiple choice question, please. You can give the answer as a direct message or just like a message in the chat, no worries. Okay, got one answer. Okay, good. Ah, very nice. Everyone's got it right so far. Yeah, come on, two more. Mr. or Mrs. T. That is correct. And who am I waiting for? Julian. Okay. Close. It's B. So you have the power. There are three formulas for power: IV, I squared R, and V squared over R. And of course, because you don't know the current, but you know the EMF. So that's good. The power is, you're going to use the third formula, is the EMF squared divided by R, and the EMF is B squared V squared L squared over R. Excellent. Okay. A triangular conducting loop with dimensions shown move horizontally to the right with a constant velocity of 3 centimeters per second. The loop enters a uniform 1.2 Tesla magnetic field, which is directed into the page. There are 75 turns on the wire on the loop. Well, the first question, define magnetic flux linkage. Magnetic flux linkage is NBA cos theta, where N is the number of loops, B is the magnetic flux density, and A is the area. Calculate the magnetic flux linkage on the loop when the loop is entirely in the field. State your answer with the appropriate unit. That's a good question. So we need the area. So this is a 6, that's 2. So the area is 1/2 times 6 times 4, which is 12 centimeters squared. That is 0.0012 square meters. Magnetic flux linkage. You know, it's sometimes written like this, N phi. So let's stick to N phi. Magnetic flux linkage is N times B times A times cos theta, which is 75 times B, which is 1.2 times 0.0012 times cos theta, which is, well, it's perpendicular. So it's perpendicular to the loop, so the angle is 0. So cos 0 degrees. And that would be 75 times 1.2 times 0.0012. 0.108. And the unit is Weber. The magnetic flux is measured in Webers. Draw on the axes a graph to show the variation with time of the magnetic flux linkage in the loop, starting from the point where the leading edge enters the region of the magnetic field. So when it touches, the field starts to the flux starts to increase. The flux starts to increase. But it starts to increase at a decreasing rate. Because it's traveling at the same speed. First, it increases by this much. In the second second, you can say in the first second, it increases by this much. But in the second second, it only decreases by this much. And actually, there's a factor of 3. Okay. So in 1, 2 seconds, so it increases at a decreasing rate. So in 2 seconds, it enters the, sorry. Actually, you know what? 1, 2. 1, 2, 3, 4. At a decreasing rate, and then it is constant. Because after 2 seconds, it enters the field completely, and that's it. That's the flux. And the maximum is 1.2. After 1 second, after 1 second is 0.9. 0.9. So that kind of makes sense, Webers. Okay. Makes sense so far? You have a very similar question in the assignment. I hope you've seen it. It's slightly harder. Like this one. Here, there's another thing that you have a resistance which is R here, and resistance is rho L over the cross-sectional area, and the L is reducing, right? So the resistance of the circuit is decreasing, and that's why you have a current. The current is constant. Okay. So even though the EMF the flux is decreasing at a reducing rate, the resistance drops, and that compensates. So here what you need to do is imagine, what if you move a small distance? What's the change in area? dA d t question mark. So I can, you know what? I think I can do a better job here. Of course, I've made a sketch, but That's not good enough, at least in my book. So let's say we have the triangle. We know that this is 6 centimeters and this is 4 centimeters. Let's say that a small portion of the triangle enters the field, and this is dx. So the change in area, dA dt, is equal to dx multiplied by the width. Let's call it y. Y dx over dt. The y, the width of this piece, will be proportional. Would be proportional to the length. So in time t, you travel a distance vt. Vt is the distance traveled by the triangle. Distance traveled. And then this width is going to be y. Well, you know what? It's going to be like this. So y is the width. So we start with a 4, and then we end up after 2 seconds. T. After 2 seconds, it's like this. So it decreases. Y decreases linearly with time. So we can figure out the formula for t. So it's going to be 4 minus 0.5 t. Okay. So I worked out the formula how y changes with time. Y is the width of this rectangle. I'm approximating a slice of triangle with a rectangle. So it's going to be 4 minus 0.5 t. Yes, you are correct. Sorry. Thank you. At least you're following. That is a very good sign. Thank you. 2t multiplied by dx dt. But dx dt is v. Well, so it's 4 minus 2t multiplied by v. Okay. So the flux d, well, a. So I'm just going to rewrite dA dt is 4 minus 2t times v. And I'm going to multiply everything by t. So dA is equal to 4 minus 2t v dt. And I'm going to integrate that from 0 to a. Well, it's from 0 to, 0 to a. And here it's going to be from 0 to t. And that's going to be a equals 4t minus 2t squared over 2 times v, because v is a constant. So a is equal to v multiplied by 4t minus t squared. Okay, and the flux is of course b times a, which is bv 4t minus t squared Yeah, this is only true for t from 0 to 2. And so that is a parabola. And if you sketch this parabola, so it's 0, 0. 1, 1 is 3. 1 is 1, 2, 3. 2 is 4. And here you go. And then it goes like this. Beautiful. So flux time. Okay. So yeah, that's better. I'm more pleased with myself now. It's not just the shape, but now I've got the mathematical result. You need to do a very similar thing, but in your case, the t's will cancel. In this, the t's will cancel because the current will also depend on the resistance, and the resistance is going to be changing. So that's another whole layer to that problem. That's why there's a star. The next one, calculate the magnitude of the induced EMF of the loop for the period where it enters the magnetic field. Well, the average, so the EMF is d phi delta t, the average. Well, that's going to be, the change in flux is 1.2 minus 1.2 Webers divided by time, which is 2, so 0.6. So here, 0, 0.6. So while it's changing, it's like this, and then it stops changing. It goes like this. But that's the average. I don't like this. I don't like this because it's changing and then stops changing. But it's not changing at a constant rate. So let's do better. d phi dt. We differentiate that, and we find that it's bv multiplied by 4 minus 2t. So it's but it's minus, EMF is minus that. So it's going to be bv 2t minus 4. So clearly, this is going to be minus 0.8. And it's going to go like this. And it's going to be 0 at, yeah, it's going to be like this. They are approximating. Okay. Oh, just a second. Okay, so a conductor coil is rotating around a fixed axis in a magnetic field. As a result, an alternating current is generated. Which graph will represent the variation of the power output when the frequency is doubled? Well, let's have a look. So what's going on? You have a coil. You have a coil of wires. And it's rotating. It's rotating in a magnetic field. The flux is BA cos theta. But theta is changing because the coil is rotating. The theta, the angle, would be changing as omega multiplied by t, where omega is the angular speed. If the angular speed is omega, omega times t is the angle of the turn. So this is going to be BA cos omega t. That means that if you want to find EMF is minus d phi dt. It's minus the derivative. So it's minus BA, which are constant, because the area of the loop is constant, times cos omega t, which is omega sine omega t, with a plus. I've differentiated, I've used the chain rule here. And as you can see, that what happens to EMF if the frequency is doubled? Can you tell me based on this equation alone? The maximum value doubles, yes. EMF maximum value of the EMF doubles. Of course. And that means, but the power is EMF squared over R. That means the power is quadrupled. So if the frequency is doubled, that means the power is quadrupled. So it's not this one, not this one. It's either this or this. Well, the frequency clearly doubles. So it's D. Okay. Now this is a very important result. Please make sure you remember it. Let's check if you understand it. So let's look at this. So this is a graph. Give me the answer, please. A, B, C, or D. C. Yeah, absolutely. It is C. Because the voltage will double and the frequency would halve. Okay. I was looking at Macron's Faraday's law and saw the curl of the E field is the negative partial derivative of B. No, it's Biola, that's the if you have a changing magnetic field that induces a changing electric field, and a changing electric field produces a changing magnetic field, that's an electromagnetic wave. That's how an electromagnetic wave works. So a changing electric field produces a changing magnetic and vice versa, and that's how they support each other, and that's why they propagate through space. Now, problem set. Oh, this is my favorite part. This is my absolute favorite part. Uh, let's consider a very simple circuit, like a battery and a switch and a nothing. I haven't talked about inductors yet, so don't worry. Look at a very simple circuit. A battery, a switch, and nothing else. Well, if you flick the switch, well, you're gonna have an infinite current. Like you'll have an infinite current from the to begin with. So it's just infinity. So current is EMF over R. So EMF over 0. So that's infinity. You have infinite current. Which doesn't make any sense. Like even if you, like, it has to increase gradually. It can't go just jump from 0 to infinity. It has to gradually increase. That's one. Hold that thought. What if I take one of the wires and make them into a coil, just like that? There's still no resistance, but what if I make them into a coil? What do you think would the behavior of current versus time be now? Just any ideas? Resistance is still 0. Aha, someone's jumping ahead of this themselves. No, it's not a sine wave, but good try. Current. So there's resistance is 0. There is a property called inductance. We haven't discussed this property, but it's there. So no coil, it just goes infinity. No coil. It goes to infinity. We don't know how quickly, but towards infinity. But with a coil, it actually goes like this. And to prove this, I'm going to use a circuit. So this is called a loop. If I click on it, inductance is 5 Henry, whatever that means, but there's no resistance. To prove that there's no resistance, I will connect a resistor, a battery, and I will measure the voltage, and I'll measure the current, And you can see that the resistance is voltage divided by current, therefore the resistance is 0. That makes sense, right? Okay. So there's no resistance. So let's do a current chart. It's a current versus time graph. And I need a switch as well. So I flick the switch and watch the current graph. Just goes up. It increases, increases, and increases. So let's watch it again. The current slowly and gradually increases. And the rate of that increase depends on the number of loops. So if I were to increase the number of loops that increase the inductance, increase the number of loops, and I close the switch, it will increase but less quickly. Okay. Now, something even more bizarre. If I take a light bulb and connect it to here, we'll need a switch. Exactly. With no coils, it's just having one coil is equivalent to having one coil-ish, or almost equivalent. But well, it is linear, it's just very, very quickly. It goes go crazy. Now, let's, if you have this setup. So let's close the switch. That causes the current to increase. Now, if I connect the lamp, well, it works because it's connected to the battery. But the lamp is in parallel with the battery, so it works. What do you think would happen when I disconnect the battery? Not only it will work, watch carefully. 3, 2, 1. It would go super bright. And then, yeah. Let's watch the voltage. Let's close the switch again. The voltage on the lamp is 9. I think it was about 40% last time. And now watch the voltmeter, please. 3, 2, 1. The voltage was 320 volts. Yes, using a simple coil, you can achieve immense voltages. And I'm pretty sure that this is how the car spark plugs work. Spark plug in a car, spark plug. So this is a spark plug, and in the car, so yeah, in the car. So it's used to ignite the petrol. It's used to ignite the petrol. But you know that to make a spark, you need several thousand volts. If you didn't, now you do. To make a spark, an electric spark, you need several thousand volts. And they use induction coils. There's a special induction coil that produces this high voltage inside a car to make the spark for the spark plug. You need several thousand volts. So yeah, I learned it. I learned it the hard way. I had a moped and I thought, ooh, my spark plugs are not working, so let's test them. So I was holding it in my hand, not realizing that on a damp day, several thousand volts can easily penetrate a thin layer of rubber. I received one of the worst electric shocks in my life. So do not hold a spark plug whilst trying to start a motor. So yeah. So what's the question? So is this effect always happen with a normal one loop circuit? Yes, you can make a lighting with a big enough conductor. I think so. Yeah. Why not? But let's get to it. An inductance. An inductance is a special property of a wire. Any wire has inductance. Even a straight wire has inductance. But it depends. Inductance L is inductance. It is a property of wire. Depends on geometry. In simple words, inductance is the ability to store magnetic energy. Ability to store magnetic energy. And that's what's going on here. This coil is a storage of magnetic energy. And when you close the loop, it is absorbing more and more energy. And when you open the switch, this energy is released through the lamp. So it builds up energy. It's like a capacitor for magnetic energy. The inductance of a coil, the EMF induced. So when you try to change the current through the coil, it will build up a magnetic field inside that will try to that will produce an EMF in the opposite direction. So self-inductance. When the current through an inductor changes, it will induce an EMF. So once we close the switch here, write down Kirchhoff's second law. Kirchhoff's second law, well, it's very simple. The EMF would be equal to the voltage on the inductor. So this is the voltage here. So the EMF is plus minus. Now the inductor will try to oppose the increasing current. So the current is increasing, so the inductance will try to produce a current in the opposite direction. So it will induce an EMF in the opposite direction. And the EMF induced in an inductor is minus L, which is the inductance, which is measured in Henry, di dt. Okay. So here, EMF is minus, well, not minus, because it's in the opposite direction, so it's plus L di dt. And now if I multiply by dt, I get EMF dt equals L di. I integrate from 0 to t, from 0 to I, and I get EMF times T equals IL. So current is EMF over L multiplied by T. So here you can see that the current is proportional to time. So the graph is like this, current versus time. So I've solved L as an innate property of, well, not of a material, no. It's a property of a wire. It's determined by the geometry. It's not determined by the material. A copper wire of the same geometry will have the same inductivity as a I don't know, magnesium wire or whatever, aluminium wire. It doesn't matter. It's only determined by the yeah. This one, so once again, using Kirchhoff's second law, that the EMF of the battery plus the voltage on the resistor plus the voltage on the inductor is 0. Now EMF is plus minus going this way, it's pushing electrons that way, but the resistor is pushing the electrons the other way. Well, it's preventing electrons, so it's pushing them back, it's producing resistance. The current is increasing, so the inductor is also pushing the electrons in the opposite direction. So we can write EMF minus VR minus VL equals 0, right? Because EMF is pushing one way, and the resistor and the inductance are pushing in the opposite direction. EMF minus IR, because that's the voltage on the resistor, minus L di dt equals 0. And now I can write L di dt is minus IR plus EMF. Now I divide by this, so I get di divided by minus IR plus EMF equals dt L dt. All right, now I integrate from 0 to I, and here from 0 to t. I get t equals L logarithm minus IR plus EMF minus logarithm EMF. Sorry, I'm rushing a little bit. So if you're not following the maths, I'm very sorry. Please come back to the video. EMF. Now there's a minus 1 over I here. So, and I multiply this. So logarithm of minus IR plus EMF divided by EMF equals minus RT over L. Now, minus IR plus EMF over EMF is E to the power minus RT over L. Multiply this by EMF, minus IR plus EMF equals EMF E minus RT over L. I is equal to EMF minus EMF E minus RT over L over R. In other words, current is EMF over R minus EMF over R E minus R over LT. So current from time is EMF over R 1 minus E minus R over LT. If we sketch this graph, time, and this is current, the maximum value, as if t goes to infinity, this tends to 0. So that's the maximum value, that's EMF over R. And the current will go like this. From 0 to... Okay. Let's see if that is true. Let's build that circuit and see if if it actually gives us that that result. Oh, sorry, current chart. And the switch, battery. Okay, close the switch. Oh, sorry. Forgot the resistor. Okay, so watch the current, please. So, bam. Does happen. That is why when you flick the switch, when you flick the switch of a light bulb in your house or whatever, you intuitively know that the current doesn't go like this. The current doesn't jump like this. This is a no. Current doesn't behave like that. Current behaves like this. And you know this on an intuitive level. That's a yes. This happens because the wires have an inductance. Even a straight wire has inductance. And especially if it's a light bulb, if it's a filament lamp, it has all those curls. Yes, it produces a magnetic field. All wires produce a magnetic field. You need time to build up that magnetic field. And that is why an instantaneous change in current is not possible. Just like an instantaneous change in speed is not possible, an instantaneous change in current is not possible. So the second one I've done this the circuit. I mean, okay, you can't access assignment 4 on Canvas. What happens when you try? Can everyone try? Has anyone managed to access the assignment on Canvas? Because that's not the first time I've seen people saying that, but I've tested it and it worked for me. Okay. Oh wow. Okay, I will fix that. I will fix that. I'm very sorry for that. Um, I'll put in a link. I'll upload the assignment and I'll to our website, and I'll post a link in a few minutes. I really hope I managed to introduce you to the wonderful world of electromagnetic induction. It is an absolutely fascinating topic. So enjoy doing the assignment. And yeah, so I'll see you. When do I see you next? On the 21st, and in a week time. All right. See you.